Hello, Calc. We've got a new topic for tonight, and we're watching this after Wednesday's class on the 12th, and it's a new one we're not reviewing anymore, and it's called differentials. Differentials are very close cousins to the derivatives, so we will observe them and their uses tonight. So we'll start out with when you have a function, just a regular old function, y equals f of x. We can think of that, when we take the derivative, we can think of it as dy dx, we've seen that notation, equals f prime of x. We've seen that notation, both of them indicating the derivative of this function. So, in this form, we are speaking about the derivatives. So we've seen that plenty of times. If we think of this as very small changes in y divided by very small, infinitesimally small changes in x, we can use them or look at them as algebraic quantities. So I'm going to multiply through both sides by the very small quantity dx. When I multiply through by it, it disappears from the left and it appears on the right. Now, this is referred to as a differential. So see how I said they were close cousins? Have a lot of the same information in them. So this differential indicates that this is a very small change in y, and this is a very small change in x. Alright, so let's see, we're going to use them to approximate the values of certain functions, and we're also going to use them to approximate small changes, or even call them errors. So we'll see how that works. Great. We're going to find a formula, first of all, for approximating the value of a function. To approximate. We're not going to use them to approximate the value of just any function. It's going to be a certain kind that this is going to be useful for. But I'll get to that in a minute. More like when I do an example. So let's look at this. Does this make sense to you? The derivative equals the limit as change in x approaches 0 of f of x plus change in x minus f of x divided by change of x. Oh well, doesn't fit this tune anymore. I used to call this h, but I just replaced it with change of x because we're thinking about differentials, which are very small changes in x. So that is the definition of the derivative. We're going to kind of drop the limit, and when these change of x's are small, when change of x is small, then we are going to be very close to f prime of x without taking the limit. So again, we are approximating, but they're going to be very good approximations without the limit. So when change of x is small, we are going to drop the limit, and now this really isn't equal anymore. It's approximate. So we use the wavy equals line. So that's a symbol for approximation. So let's solve this for f of x plus change of x, because that's the kind of functions I want to approximate the value for. You'll see. So let's go ahead and remove everything and put f of x change of x by itself. I'll put it on the left. When you, again, this is not equals, it's approximating. So it'll turn out to be f of x plus f prime of x, change in x. Algebraically, this can be rewritten as this. And that is, you can verify that. All right, that is going to be used, again, to approximate the value of a function when we know f of x, but we don't know f of x plus change in x when change of x is small. So makes more sense when you see one. So I want you to approximate the square root of 9.01. And we're going to use differentials to do that. So we're going to use this formula, and recognizing that we use it when the function we're asked to approximate is just a little different from one that we know. So we know square root of 9. So I'm going to think of our function as the square root of 9. And of course, before we put the 9 in, it's just the square root of x. So the square root of, so the function evaluated at 9 is the square root of 9. And then we're going to have the change in x. It's going to be the 0.01. Alright, so with those thoughts in mind, I'm going to use this formula to approximate that. So I'm going to go right down the formula from left to right. The function is the square root of x, 9 plus 0.01. So that's what I'm trying to do. It's going to equal approximately the function, the regular function of the one we know, square root of 9, plus the derivative of the function. Well, the function was the square root of x, which is x to the 1/2. So f prime of x equals 1/2 x to the minus 1/2, which we write as 1 over 2 x to the 1/2, or 1 over 2 square root of x. Alright, we've done that one numerous times. So our x value, as we have seen, is 9. So I'm going to write this next plus the derivative, which is 1 over 2 square roots of 9 times change of x. And the change of x is this value right there, times 0.01. So we are approximating without the derivative. So we are using derivatives, approximating without using a calculator to plug in 9.01 square root. So we can do all this pretty much by hand. So we get the approximate value of 3 plus 1 over 2 times 3, which is 6, times 0.01. So 1/6 times 0.01. I did use the calculator for that, and I got 0.001666667, and 3 plus that is 3 plus 3.001.6666667. So the square root of 9.01, using this method, it comes out to that. If I do put this in the calculator, I get what it's really equal to, and 3.001666667. So, nope, that's not right. 3.01666, and then it divides, I'm sorry, I wrote the same thing. It's 204. So it was same through all of these decimals. So that's a very close approximation. It does equal this, and this is very, very close. So there are times when it is quicker and less cumbersome for very difficult or very crazy things to find the regular function in. This will simplify things in certain cases. So this is sort of a training ground.